We present MV-DeepSDF, implicit modeling with multi-sweep point clouds for 3D vehicle reconstruction in autonomous driving. Reconstructing 3D vehicles from partial point clouds is of great significance to autonomous driving. Recently, implicit modeling has been utilized to tackle this problem. The implicit modeling represents an object with a continuous function, such as the sine distance function, which supports 3D mesh extraction at any resolution. Unfortunately, previous implicit modeling methods mainly focus on recovering 3D shapes from a single-view partial point cloud with trivial noise. They fail to leverage the multi-sweep information of vehicles, which is usually available in real-world datasets. Furthermore, they produce low-fidelity results when applied to the noisy and sparse in the wild point clouds. In this work, we propose a novel framework, dubbed MV-DeepSDF, to exploit noisy and sparse multi-sweep partial point clouds and implicitly generate high-fidelity 3D reconstructions of vehicles for autonomous driving. We simplify this task into an element-to-set feature extraction problem. We infer an optimal estimation of the 3D shape described in the abstract implicit space. The overall framework of MV-DeepSDF is shown in this figure. There are three main steps. Namely, preprocessing, optimal latent code prediction, and 3D mesh extraction. We adopt DeepSDF as the baseline model. In DeepSDF, the 3D shape is represented by a one-dimensional latent code. Given a 3D querying position, the DeepSDF decoder can predict the corresponding SDF value. The following figure shows 3D reconstruction results given by DeepSDF under different given point clouds. To utilize multi-sweep point clouds, we first analyze consistency and complementarity in the latent space. We propose that compared to the ground truth latent code, an individual latent code is composed of similar, different, and error components. For the similar components of any two individual observations, it can be divided into three situations based on the properties of the observations. First, they have completely different information. Second, they have some different information. Third, they have redundant information. To approach the ground truth latent code, it is desired to aggregate all consistent and complementary information among all individual latent codes and predict the regions not captured in the multi-sweeps. We design an architecture to optimally estimate the ground truth latent code from multi-sweep point clouds and their corresponding latent codes. Inspired by PointNet, which learns a global feature for each point cloud that aggregates complementary features from each individual 3D point feature, we transform the problem of shape estimation in the implicit space into an element-to-set feature extraction problem. Our architecture concatenates the global features extracted from the shared PCN encoder and latent codes obtained from DeepSDF decoder to generate the element-level representations. Then, we employ average pooling and mapping to aggregate the element-level representations into a set-level predicted latent code. We adopt a curriculum training strategy. In Stage 1, we pre-train the DeepSDF decoder using watertight CAD models belonging to the car taxonomy of the ShapeNet v2 dataset. In Stage 2, the network is trained to reconstruct 3D vehicles from multi-view partial point clouds and their corresponding latent codes. To reduce the domain gap between training instances and in-the-wild instances, we employ a technology called PCGen to produce partial point clouds. PCGen places a virtual LiDAR with real-world parameters around the vehicle and simulates the point cloud captured by the virtual LiDAR. We compare our approach with four state-of-the-art methods, including three implicit modeling-based methods: DeepSDF, CDeepSDF, MNNet, and ADA pointer. We employ asymmetric chamfer distance and recall as metrics. Note that with multi-sweep point clouds, competitors generate multiple reconstruction results, so we compare with the best single-shot reconstruction result, which is the mesh with the minimum ACD among the multiple single-shot reconstructed meshes. Furthermore, we report the results of DeepSDF and MNNet with multi-sweep inputs, denoted by MS, in which we stack the partial point clouds of multi-sweeps into a single point cloud and perform single-shot-based reconstruction on this stacked point cloud. As seen, on Waymo dataset, our approach achieves the best reconstruction results both qualitatively and quantitatively. On Kitty dataset, our approach also yields the best performance. The proposed MV-DeepSDF is a general framework that can be extended to other taxonomies. Following the pipeline introduced in this work, we evaluate on indoor sofas of ShapeNet v2 and outdoor cyclists of Waymo and show that our method is versatile. Thanks for your attention.